Hi, I'm Ben-Yaakov. This presentation is entitled The Effect of Package Size on Ceramic Capacitors Parameters. This is a joint work of Yivgeni and myself, and I'm going to do the presentation. There are some related videos which are shown here. Here are the links. I'm going also to print the link on the YouTube page of the video that you are now watching. There is a disclaimer here that the ceramic capacitor and manufacturers mentioned in this presentation are for educational purposes only. There is no endorsement or recommendation implied, and also that there are many other companies making similar capacitors, but only 2 manufacturers are included in this study. So in this presentation, I'm going to talk about the effect of package size on basic ceramic capacitor characteristic, the effect of package size on the derived parameters, that is, parameters that you calculate from the basic characteristic, and then inconsistency in manufacturer's data of ceramic capacitor and inconsistency of data between 2 manufacturers. And then at the end, I'm going also to cover the effect of DC bias on ESR. The ceramic capacitor size are usually given in either a metric notation here, shown here, or the EIA, which is by an inch. The 2 first numbers are for the length. Here is 12, this is the in mils, that is 12 mils of an inch, which means that here it is translated to 3.2 millimeters length, here the 3.2, and the width shown on the second 2 numbers. And this is like 10, which is 2.5 millimeters, and here the 2.5 millimeters. So this is the notation used. Notice that there is no indication on the thickness, and the thickness may vary between packages and in fact between manufacturers. Now, recent ceramic capacitors, the multi-layer capacitors, are rather complex and intricate, and you have electrodes. This is a cross section. You have electrodes, and you have the dielectric material in between. These are the contacts, and of course, consequently, the equivalent circuit is not simple. We have capacitances, and then we have in between actually inductances, so it's a sort of a distributed system. It's not a basic, simple, discrete system, but we usually describe this as a lumped circuit with 1 capacitor, ESL, and ESR. In this study, we have included 2 materials. One is the C0G, or NPO, which is designated as a class 1. This is a paraelectric material, very stable, but it has a lower dielectric constant as compared to the ferroelectric material, which is denoted as the class 2, which is less stable material but has a higher dielectric constant, and consequently you can build capacitors of larger capacitance at a smaller size. So these are used for large capacitances, and these are better capacitors, but they are limited to a capacitance of about 0.1 or maybe up to 1 microfarad, and then you have to move to other material. X7R is probably the most popular class 2 material because of some reason. One of them is that it is less sensitive to temperature, and this is the only one we have included. There are many other units here which we are not discussing. So if you look at the datasheet of a typical ceramic capacitor, this is what you're going to see. This is the size area, and then the material. In this particular case, it's X7S, which we are not discussing in this presentation. This is just for an example. And then some information about the capacitance, the tolerances. And here are the graphs which are very, very important. One of them is the dependence of the differential capacitance as a function of the DC bias. This is a 100 volt capacitor, and you can see that at, say, 50 volt, it's going down by 70%. So only 30% of the capacitance is left. So this is very important. And then we have the ESR, the blue one, which we are going to discuss. This is the impedance as a function of frequency which is less important, but the ESR as a function of frequency is very important. And then we have the resonant point when the L and C are resonating, and the impedance of these two is about 0, and you are left with the ESR. So here is what we see, that you see the ESR. So this is the resonant frequency, which of course is a function of the capacitance and the inductance. And then we have the current that is allowed, or the expected temperature rise per a given current. This is the current, and this is for different frequencies. These are the parameters that we are going to discuss in detail, and then a derivation of parameters based on these basic primary or generic parameters. First thing to look at is how is the differential capacitance changing with the bias. So here we have a 100 volt capacitor, and see it's 50 volts halfway. You see that there is a big difference, and these are different packages. All of these capacitors are 1 microfarad, 100 volt. To see it better, we have this graph here. These are the packages, okay? Here is the drop in capacitance. In this particular case, this is 100%, and then it goes down. You see that for this package, the smallest of this collection, it goes down to 0.4 of 1, so it's 0.4 microfarad in this particular case. So 1 microfarad, and this is at 50 volt, halfway of the 100 volt maximum of this capacitor. Interesting that at this point here, we see that it goes up again and then it drops again. Well, in this case, perhaps we can explain it in the following way. If you look at the packages, you see that in this case, the width is 25 mils as compared to 12 here and 20 here. So perhaps the fact that the width is larger makes it less sensitive to the voltage, so the drop in the capacitance is lower. One possible explanation for this dependence is the electric field that is imposed on the ferroelectric material, and it has to do with the thickness of the layer, and therefore if the thickness is smaller, then I would guess that the electric field is larger, and therefore you'll see more of a change as a function of the voltage. So here, if the width is larger, then maybe there's a change in dimension which makes the difference. So in this case, we can offer an explanation, not so in other cases. So here it is. We see it here for 1 microfarad and 10 nanofarad. We see a similar behavior. This is a similar behavior. This is percent change. So in this case, in this particular case, we see this increase, which again perhaps can be explained by the difference in the width of this package. But if I look now at other capacitors, by the way, this is the C0G, the NPO. It's a different material from all these, so it's not fair to compare these to the others. And as you can see, this is a very stable material, and there is practically no change in the capacitance. So this is very, very nice in this respect. And here, however, here we see this bump here for the 1 microfarad, but we don't see it at 100 nanofarad. So here it is, this particular package, we don't see this change here. We see it only here, and we don't see it here. We don't have many packages here for this particular capacitance. So, well, maybe the explanation I offered makes sense, but as you can see, it's not consistent. So we don't know what's going on in here. The important thing is to be aware that for these sizes, there is almost no change for this particular capacitor, while for these sizes, there's a lot of change. This is very important to realize. And then I move to the ESR. Again, there's quite a bit of a change. All of these, by the way, are done by the PCIM, the simulation tool of Kemet. And here we see 1 ohm, and this is 0.38 ohm, 380 milliohms here. This is for the same capacitance, but different packages. So we see it quite a bit a change here. Here we see a change in the opposite direction. That is, for the smaller size capacitance, it's a lower ESR, and for the larger one, it's a larger ESR, and about the same ratio. This is 1 to 3, and this is 3 to 1. Beats me. I cannot understand this and cannot explain it. Either there is a physical explanation, or maybe there is something wrong with the simulator, which of course could also be the case. So this is the ESR, and now we move to the RMS current. The RMS current, of course, depends on the ESR. You don't see it here, but we do see for the same capacitor, which assumed to have the same ESR, which is incorrect, we have seen it already. You see big differences. 1 amp for this is 20-degree rise of temperature, and here is 0.4. While here, same package here, like same package here, although it's a different capacitor, this is 6 amp and this is 1 amp. This could be explained by the fact that the ESR here is much lower. So in order to sort of normalize it, we've derived some parameters from the basic parameter, like the dissipated power, like the IRMS squared times the ESR, and also the thermal resistance for 20 degree, which is 20 degree divided by the power dissipated at 20 degrees. So we see that for the smaller size, we can dissipate 50 milliwatts for the 20 degree, while here for the larger side, only 18. Also, I would have thought that this would be the other way around, but this is a much larger area, so you can dissipate more power for the same temperature rise. Now, same thing, you see it here. Size package, you can dissipate more power than the larger size package. Okay, it's a factor of 4. Now, if we calculate the thermal resistance, again, it's very difficult to compare these two because it's different material, but if I compare these two packages, 1825, this is 1 microfarad, this is the 100 nanofarad, you see a very big difference. Here we are talking about 370 degrees centigrade per watt, and here it's only 50. Very strange. Maybe the thickness can explain it, because 1 microfarad is probably thicker than the 100 nanofarad, but still this is a very big difference, and this is something one has to be aware of. Now I'm moving to the resonant frequency, which is given, which you can find from the impedance, the drop of the impedance to about the ESR, and the resonant frequency is of course equal to 1 over 2 pi square root of the inductance times the capacitance, from which you can calculate the inductance, since we know the resonant frequency and we know the capacitance. Okay, so this can be derived and calculated. So if I look at the resonant frequency between 100 nanofarad, 1 microfarad, and 2.2 microfarad, I see the resonant frequency goes down, which makes sense, because the larger the capacitor, the lower the frequency will be for the same package, assuming the inductance is about the same. And indeed, if we look at the inductance, there is a difference, but in this particular case, it's not a very big difference for the same package, okay? So this is 1.4, this is 0.6, 1.5, and this is all for the 1812, so it's about the same. So in this respect, it seems to be more consistent than the other cases. Now I'm coming to the real issue of consistency, or inconsistency, I should say, within the data itself. So here I'm showing the temperature rise as a function of the current for different frequencies because the ESR is dependent on frequency, and this particular line here is 1 megahertz, okay? So we see that for 1 megahertz, temperature rise of 20 degrees, we can carry 4.2 amp current for a rise of 20 degrees at 1 megahertz. This is from this window here. But I can move to another window, which also gives me current, but in a different way. Now, this is the frequency, this is the current, and here is the plot, and this, all of this is for 20 degrees. Okay, this is 20 degrees rise. And if I look at 1 megahertz, I find 2.19. This is not acceptable, of course, because this is the same capacitor and the same set of data. You get 4.2 in this case, and you get 2.2 in this case. This just doesn't make sense. This is something is wrong here, obviously. Okay, so we don't understand. Maybe it has to do with the cooling or whatever. It's not understood. And then I'm coming to another issue, which is consistency or inconsistency between manufacturers, okay? So we have the TDK and Kemet. All the above was for the Kemet. Now we are examining the TDK. So for the case of 1 microfarad X7R, looking at the ESR, I find that the TDK ESR is much lower for this set of packages than the ESR for Kemet. I'm talking about same capacitance, same material, same voltage, and same package, okay? This is same package here. And then, if I look at the RMS, obviously I see a difference, but lo and behold, it's reversed. That is, the TDK quote a current which is much lower than the Kemet, while the Kemet ESR is larger. So you would expect something reversed. That is, the Kemet current should have been lower than this one. Now, obviously, or probably, this has to do with the way it was measured, the way the capacitor was mounted on the PCB, how much copper was around it. All this information is not given. We don't know what it is. So obviously, I would suspect the Kemet is measuring the capacitor while it is mounted on a PCB with a lot of copper area around it, and therefore they can pass that much current as compared to the TDK, which must have a much, much smaller copper area. Otherwise, you cannot explain this very big difference. And then we have similar differences for other parameters, and this is the ESL. In the case of the TDK, the ESL is quoted as to be higher, while Kemet is quoting it to be lower. For the dependence of the capacitance on the bias, well, it seems pretty much similar. Now I'm coming to another issue, which I think is unresolved, and that is the effect of DC bias on ESR. If you look at the PCIM data or results or graphs shown here, this is one capacitor, 1 microfarad, and it is a 50 volt capacitor, and here it is exposed to different bias voltages, 0 voltage, 25 and 50, and you see that the ESR, this is the ESR, is going down quite a bit between 0 bias and 50. Okay, so there's quite a bit of a difference here between the ESR, and it's going down, becoming less resistive. And you can see it also here, this high voltage capacitor, and the bias is 1000 volt. This is at the end of the voltage allowed, and you see that there's a big difference here, and again ESR is going down. Okay? However, in a paper that we have published at PCIM 2020, we have presented measurements on ceramic capacitor which show the other way around. That is, we have found that if you measure it with a network analyzer, in this particular case is the Omicron Border 100, this is by the way a joint paper with people from Omicron lab, you see that the resistance, the ESR, is going up with the voltage. By the way, the voltage is decreasing the capacitance. And it sort of makes sense that the smaller capacitance we have a higher ESR, which we have found here. This is not an explanation which is based on anything other than some intuition, okay? But still, the fact is that we have measured that ESR is going up rather than going down as shown in the PCIM data or simulator. And here is some summary of measurements that we have made. This is the ESR change. In all cases, you see that a change in the voltage will increase the ESR. The PCIM, for all cases that are relevant, because these are wood capacitors, we don't have data from them, but we have data from the PCIM simulator for CAMET. You see that while we measure 25 increase, the simulator shows minus 68 decrease going down. And here it is 71%, and this is minus 88%. Now this issue is unresolved. I brought this to the attention of CAMET. I didn't get any answer up to now. It's been a couple of years now. And so this is an open question that I cannot explain. Obviously, we stick to our measurements, and then you have, on the other hand, the simulation by PCIM, which shows the other way around. There's also another issue here, and that is how is the package size affecting the change of ESR with the DC bias. Now this is from the PCIM simulator, and we think that the direction is incorrect, but irrespective of the direction, we see that the package size is affecting the change. That is, for 1210, we see a change of 22, under the same condition, of course, we see a change of 22 milliohm, while for the 1805, we see only a change of 14 milliohm. So it is reasonable that the package size will also affect the change in the ESR, but again, we don't know if we can rely on the PCIM simulator in this case. So what are the conclusions here? First of all, the package size really affects the characteristic of ceramic capacitor. One has to be aware of this and look carefully at data sheets and the simulator, assuming that they are correct, of course. There is no consistency in behavior. I cannot explain all these changes that you see between the packages and between the capacitors of same package. There's also some questionable differences between the different manufacturers. And of course, the final question, can we trust the data of the datasheet? Well, this is what we have. We have to live with it. And then we have to be very careful to put in some safety factors, and whenever possible to do measurements of our own. With an analyzer, you can do measurement very nicely with a network analyzer. So it is highly recommended. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.